What's the parallel? Using index 6. Why this? Even if you had i's, subset of x for each I in I, then this is a subset. You had it, right? And over here, you also have something similar. Now let's look into the union. This example is providing us everything. Okay? So, what is so suppose if we take two such lines. Let me take, say, this one. Okay? Say this is another line, say ln. ln union ln. That cannot be a vector subspace. Okay? Why? Let's see. Here's a quick example. This one is a subspace, x-axis. This one is a subspace, x-axis. Right? But if I take the union of these two, it is not. You can do the similar over here. So why? So let's see. So for instance, (1, 0) is in this line, x-axis, and 0, 1 is in y-axis, but 1, 1 this is in neither. So the union of two vector subspaces need not be to prove a result. Remember, you need a proof. Okay? But to disprove it, you just need a counterexample. Okay? So the upshot of all of this is that the union may not be in sub of V. Yeah? But not everything is lost. Not everything is lost. Let's see. Often when something doesn't work, we have to change our viewpoint. Okay? You see this in every game. Okay? Cricket, the bowler is bowling so tough that he cannot bat. Okay? So you have to change your stance. Okay? So you have to change your way of batting. The opponent is so difficult that you cannot make a move towards the goal. So you are always trying down this route or that route. So you have to somehow change your way of attack. Right? Same thing here. This is also a game. So the union didn't work, it seems. But here is another way of looking into the union. What is it? So let's look at it in this way. Suppose A and B are subsystems. Then I know, obviously, both A and B are also subsets of A union B. Right? Now, let's think. Suppose I take I also take another subset. Suppose I take a subset of X which contains both A union B, both A and B. What is A union B? X belongs to A union B if and only if it belongs to A or it belongs to B. Right? Now if it belongs to A, by this it is a member of B. If it belongs to B, by this also it is a member of B. So it follows that if you have a subset which contains both A and B, then A union B is a subset of B. Right? Now what does these two statements tell us? It tells us that A union B is a subset of X which contains both A and B and is the smallest such. You cannot have a subset of X which contains both A and B but doesn't contain A union B. So it's the smallest subset containing both A and B. Right? So the moral over here is A union B is the smallest subset of X containing both A So this is the approach let us take. So this is the approach let us take towards tackling that here. So what is it? So let us now see that suppose, can we describe, so the problem is like this. So we have this vector space. Okay? And you have given me a subset T, not a subspace. To make it proper, let me say that the 0 is here. It is not a subspace. Can I find, the whole question is, can I find the subspace? So the question is, does there exist what happened? Oh. Does there exist a subspace of V? So the first question is this. See, to speak about this, I need first the existence, right? I need to know that there exists one, and then I can only find the smallest one, right? So does there exist a subspace of V which contains T? Remember, subspace of V already has, whatever B or V, already has two things in it. It has the zero vector space and the whole space. It's already there, right? So now, what is your answer to this? So you gave me a subset. Does there exist a subspace which is larger, which is bigger than T, which contains T? Yes or no? So, you have given me any subset. My question is it possible to find a subspace of V which contains T? What is it? V. V itself is there. Good. Very good. Now take the collection of all subspaces which contain T. Okay? And take their intersection. Any intersection is again a subspace. Right? So if you take the intersection, that will be another subspace. And the smallest one, which contains T. Right? So, immediately, so the answer to this is yes. V. Right? So, by T1, since the intersection of subspaces is a subspace, there will exist a smallest subspace of V which contains T. Okay? Because how will you do it? You take the collection of all subspaces which contain T, right? Take their intersection of subspaces is subspace, so the intersection is subspace, but all of them is bigger than T, so the intersection will still be bigger than T. Okay? Alright, good. But there is a fact. So I can actually find the smallest subspace like this, right? And this is the intersection of all subspaces which contain T. Yeah? But this is a very bad description. Okay? Why bad? Because given T, I have no information of what elements, which vectors shall be in this subspace. Right? So I cannot tell which vector is there or not. So naturally, so that's why it's bad. I want a better description. Okay? Alright, now let's try. So need a better description. Now listen carefully. So I need to find the subspace which contains T. So what do? I take you have given me the specification. So all the members of T must be there, right? It must be a subspace. So 0 must be there. So 0 should also be there. members of T. Say T1 and T2. T1 and T2 must be there. T1 plus T2 must be there. T1 plus 2T2 must be there. Okay? So lambda T1 plus mu T2 must be there. Right? Okay. So I take all the two things and their combinations. Why 2? If I take 3, the combinations must also be there. Right? So every that's it. That's it. Why? Let's now do mind check. Let me put this is the set of all finite linear combinations. And what do I mean by this? So this is the definition of my finite linear combination, right? So X is a member of span T if and only if X is either 0 or there exists a natural number T1, T2, Tn from T, lambda 1 such that X is lambda 1 T1, lambda 2 T2. Okay? So this is called this, and we will now show that span of T is a vector subspace and the smallest subspace of V which contains T. Okay? So that's our next word. Okay, liberated. So it says, the first part says, if you give me any subset of V or a vector space, then span of T. Sorry. This is a subspace of V, and span of T is a subspace of V, and if you give me any other subspace of V which contains T, then that subspace will also contain span of T. So in other words, it is the smallest subspace which contains T. Okay? Alright? Let's have a quick look. By definition already, remember what was the definition of span of T? Something is in span of T if and only if either it is the zero vector or it is a finite linear combination, right? So I force 0 to be a finite linear combination, namely the empty one. Okay, but so by definition, why am I making strange mistakes today? There should be another. Yeah. Also, yeah. Span of T is bigger than T and is a subspace of. Then, now, span of T contains, what are the members? Either x is 0 or there exists a natural number. If n is equal to 1, and I take that only one scalar to be 1, then it tells me every member of T is already in span of T. Right? So, by definition, 0 belongs to span of T, and for n equals 1 and lambda equals 1, we get that T belongs to T implies now show that it is a subspace. So already it's bigger than T, we must show it's a subspace. Non-emptiness is already done. So let and I have to show x plus lambda y is there. Now if x is 0, x plus lambda y is just lambda y. If y is 0, yeah? So, and if let me expand it. Why? If x is 0, then this is lambda times y. Okay? Now y is from span of t. Then it's either y is 0 or not. If y is 0, lambda times y is also 0. 0 is there. Already we have shown. If y is not 0, it is there exists finitely many numbers. Lambda 1, lambda 2, lambda n, t1, t2, tn, so that y is that sum, right? Multiplying by that, it is still a finite linear combination of members of. So, if not, so y would look something like this. And so lambda y is lambda lambda 1 t1, which is again in span of t, right? So that happens if x is equal to 0. If y is equal to 0 and x is not, okay, then you have already told me that x is in span of t by your. If lambda is equal to 0, so you see, so in any case, if any one of these three is 0, then you have what you have started off. You have already told me that x plus lambda y is, okay? So let's assume x is not equal to 0 and y is not equal to 0, as well as lambda is not equal to 0. Okay. Then there are natural numbers m and n, t1, t2, tm. These members coming from t, lambda 1, okay? So then x plus lambda y is mu 1, sorry, lambda and hence quite trivial. It's just that it took long to write. If it is non-zero, that means there are natural numbers, members from t and scalars such that x and y are some combination like this, right? So then what is x plus lambda y? X plus lambda y is this plus distributivity again, lambda times mu1 s1, lambda times mu2, which is again, so that ultimately that plus gives me another, so this was a this was a scalar combination of n things, this was a scalar combination of n things, x plus lambda y becomes a scalar combination of n plus n things, right? Of members of T. Again, okay? All of them are coming from T, so it's n plus n scalar combination of members of T. So therefore, this becomes a member of span of T, right? Immediate. All right. So, is a subspace. Now, let us take any subspace of V and X okay? If X is equal to 0, then already X is a member of P because P is a subspace. Okay? Otherwise, so else, T1, T2, Tn, they are members of T and hence members of P, right? But P you have told me to be a subspace. So every finite linear combination of members of P is automatically in P. So therefore, and that proves it. Okay? So, you see that span of T is the smallest vector subspace of V which contains T. Okay? Now, we will look into some quick things. It's very quick. You have to just remember this. What is span of T? T is a subset of V, span of T is a subspace, and the smallest one which contains T. Okay? Clear? Here is the game then. Observe. It follows as in particular. So, what will be this? The smallest subspace. And what is it?
Smallest subspace of V.
Smallest subspace of V. Right? It is the smallest subspace which contains the empty set. So it must be the smallest subspace. Okay? And what is the smallest subspace? 0. Good. So span of this is 0. So it says span of T is equal to T if and only if T is a subspace. What new is this? if span of T is equal to T, span of T being a subspace, equality says to T is a subspace, right? And on the other hand, suppose if T is a subspace, already T is a subspace. You have told me that span of T is bigger than T. Okay? And the smallest subspace which contains T. Alright? That's we have proved now. Okay? But you have told me T is a subspace already. So span of T cannot be bigger. Actually bigger, it must be same. Right? Because T is a subspace containing T. Right? So therefore, you see the triviality in this argument. Once you see this, that the span of T is a subspace and the smallest subspace containing T. Okay? See, immediately, you don't need to prove. Okay? So, in particular, span, can you tell me what will be the span of T? Think. What is span of T? No, it's subspace bigger than T. Alright? Then I have said I'll take the span again. So it will be look at B. It says span of something is equal to it if and only if. Alright? The span of T itself is a subspace. So this should be equal to the span of T. Right? Span of span is span. So this is this clear? It's not T, but it is a span.
But can't you only just say that T equals to T?
Why?
Can't you say that C equals to T?
Why?
Because of, remember, we're given that in B that the span of T equals to T.
These are separate, sorry. These are separate assertions. So, A and B, when I'm speaking about C, it is not that I am in continuation of B. It's another assertion. Right? So, here I am saying span of T is equal to T, even only if T is a subspace, but here I didn't mean that span of T is. Okay, clear? Now, so one minute. Try to get hold of this picture. Let me try and explain. I find this kind of a viewing very. Whenever I am drawing with bold, it means I can see it. Okay? Remember, in a vector space, I can only see subspaces. Because subsets are somehow intangible. Okay? So, it's something like this. This was your T. When I draw it like this, it means that it's not completely visible, but I can see, right? As if I'm trying to explain, okay? And then, when I make it into a subspace, this is my span of T. Okay? So it's bigger. Now it becomes visible as a subspace. Okay? And it is the smallest such which contains this T. Okay? Now, what I want to say is, so it is so you do it twice, you get back what you do it once.
So can we say for C, span T equals to span T, even only span T is an element of sub V?
Yes, but span T we know is an element of sub V. That's why the equality holds. Right?
Okay. But there is written that on the equation, on the operator, written that T is the subspace of space.
Subset of span T.
So there, yes, there should. I'm thinking. I'm thinking that that should be T. When you're calculating the span T, the molecular, we are calculating span T. Once then it become that thing that inherent packet on the side. When you put T there, it's going to be the same span T that has.
Will I put T in place of this?
Yes.
No.
Because that thing.
Wait. I am saying over here that span applied on the span. So that's why I drew it like this. So if you had the subset like this, you expanded it and become a subspace. Okay? But subspace is also a subset. Right? You want to see if you can expand it further by taking span. So this is saying no. This is it. You stop over here. Okay? You cannot go any further by taking spans. Right? So that's why I drew it. So it's as if from becoming half visible to becoming completely visible in the domain of vector spaces, right? And subspaces. So when we can only see subspaces, we can only have a feeling of a subset, but we are only sure about subspaces. Right? Okay. So now, you cannot go on taking span. Once you hit it, then it's closed, right? That's what it is saying. Okay. So now let's see. What can we say about this? Or even earlier. Suppose I take two subsets. Can you see that? Right? Because span S is already bigger than this. That is a subspace which contains T. So span T should be smaller than that. Okay. So therefore, can you see that span so what shall be the connection between span A, span B, so what shall be the connection between these three things? Can you say?
Don't they intersect?
Huh?
Don't they intersect?
Okay, let's see. This one tells me that since A is a subset of A union B, right? So span A is a subspace of span A union B. Similarly, span B is a subspace of span A union B, right? So both of them are contained here. Okay? Right? Now let's see. Can I see what else is there? How big is this? Yes, that's mine. So, okay, let's first initially stop here and then we will come back to this. We will see that there is a connection here. Okay? So why did I bring in this span? Well, so let's start off with this picture. let's start off